Good afternoon. I think that what I'm going to present today relates back to 30 years of doing adaptive management. And it's your responsibility to figure out what I'm about to say is actually relevant. I'm not going to talk about phosphorus. I am going to talk about participatory modeling, which is part of the overall modeling effort. And I don't know if you've actually seen national PBS the clapping that's associated with doing a spectacular view. When they do the news, they have a person who's devoted their career to a particular aspect, and 40 or 50 years of what they've been working on it's down to 10 minutes. That's why I've named. So 30 years of my life is now down to 10 minutes. But I think it's relevant for three reasons. From what I'm hearing all day today, one of the things that I'm about to present is relevant because of your appreciation of the need for models. Because it's relevant because it's human nature to divide into silos, and I heard the word silos used today. And I also heard that it's relevant for your need for metrics and integrated monitoring. So the outline for today is first, let me explain what it means to do participatory modeling and why is it needed. I'm going to give you three examples from the Everglades of conceptual modeling, physical experimental modeling, computational modeling, and then to end, we'll talk about the strengths and weaknesses of participatory modeling. What is it? It's a series of workshops that give stakeholders, resource managers, engineers, and scientists with the power to influence the scope, scale, and implementation of a policy. Just like those masked characters off to the right. How does it work? Its workshop leadership provides an overview of the problem, and scientists and engineers provide stakeholders with a modeling tool to assess and evaluate problem-solving options. We need to do it when two or more of the following are needed. One, there's false narratives, misconceptions, or confusion about the problem. There's potential for cultural or economic impacts. There's a poor understanding of the ecology. There's a high degree of uncertainty or risk. And there's a history of non-participatory decision-making, or there's a desire to build consensus and key to, at least in Florida, avoid litigation. The first example I want to give you is associated with tree islands. This is a section of the Everglades. It's about 500,000 acres in the center of the Everglades, showing in green the tree islands. Tree islands range between 1 acre in size and 10 acres in size. They are the biodiversity hotspots of the Everglades. They are phosphorus sinks for the Everglades. They keep the phosphorus concentrations in the Everglades below 10 parts per billion. That's a B, not an M. And the question we have is, how did this happen? You're about to see a transition from 1940 to 1995. Everything in red is gone. 60% of all the islands in this particular section have now disappeared. So there's a need for participatory modeling, and it was driven by false narratives and misconception or confusion about why they disappeared, the potential for economic, and in this case, cultural indigenous knowledge of the impacts, and a poor understanding of the ecology. So we develop conceptual models because it gives us a better understanding of knowledge. It focuses on socioeconomic and scientific debates. It creates a forum for stakeholder participation. It has the potential for consensus building. It prioritizes research dollars, and it facilitates adaptive management. So the first thing we did with tree islands, we built a conceptual model. And I'm not going to show you the whole model all at once because your eyes would glaze over. So let's step through what a conceptual model looks like when we first started doing Everglades restoration 30 years ago. At the top of your model are the external drivers, three simple things: climate change, compartmentalization of the Everglades, and water management. What follows are the series of stressors. All the stressors on the system, like exotics, salinity, nutrients. And then the interaction of those drivers with the ecological structure of a tree island. A little complicated, but nevertheless, it's showing that the vegetation on those tree islands is a function of fire frequency, of water hydrology, feedbacks from soil accumulation or erosion. And then finally, all that leads to attributes. The attributes of the system are with the things that you measure to see if you are succeeding in your restoration efforts. Now, this conceptual model, when it was first published, didn't have the numbers on it. The numbers were added to be part of a participatory modeling effort in which everyone was invited to do three things: to understand the importance, to understand the linkage, and to understand the ability to predict those linkages. So we had clickers in everyone's hands to evaluate their opinion. And then you can see here that if it's a green color, it means we have a really good understanding of that linkage. If it's red, we don't, as an example. So that now that conceptual model turned into this. Very hard to read, but it gives us things to focus on for our monitoring effort. For example, in the middle here, what you see is that soil oxidation and fire frequency is impacting the vegetation structure. But most important, we didn't really understand the soil dynamics, and that's why you have a dotted red line. Similarly, the hydrology is affecting the vegetation structure, which in turn is having a major impact on the wildlife. So we decided to measure soil accretion rates on tree islands to see how it's being affected by hydrology, and we monitor the wading bird nesting component of the animals living in the tree islands. Now, you saw this image earlier. This is the adaptive management sequence. So the question is, where is participatory modeling in this whole process? Well, clearly it's input from the science panel and the research modeling support, which is where we're at right now. Now, what we did with this, we actually turned this into an active adaptive management program, an experimental program. A physical model was designed with stakeholder input, which I might add took many years to develop. We named the different outputs, the different designs after models, car models. And we actually had a Ferrari model, which came in at $4 million. And in the end, we decided to go with a Prius model, which was going to be supported by multiple state agencies, but in the end, they backed out, and we ended up, the science effort put in brand new culverts to evaluate one of the key uncertainties in Everglades restoration. Everyone hears about the need to improve flow in the Everglades. Probably you all heard that. And it was really interesting to me that no one had ever measured the velocity of the water to see what is the velocity needed to restore the Everglades. And so this particular adaptive management experiment was designed to understand the impact of flow. What is too fast or too low? And I'm not going to go into that because that is a big study, but I will say one thing. What we discovered is that if the flow is too great, we defy the 10 parts per billion threshold for phosphorus, that the loading rate increases and you actually have a detrimental impact on the Everglades. So the feedback comes later. So what we found from this whole physical model that we created that's been 10 years that it's now done after 10 years, it feeds back to other aspects of the restoration effort. And then the thing is, most important in the entire system is actually what we heard today in a variety of the models that you're using, is that the computational modeling is probably the most utilized, it's the most important. And we designed an environment kind of like this where we have roundtables, where we would have a workshop, where we would hand everyone a map of the Everglades. And we would say, for this part of the system, you have these kind of options for changing the system. You have culverts here, you have pumps here, you have land use management here, best management here, you get rid of sugar farmers here, you increase farming over here, you move everything around, and we had we turned all that information into computer code. Here's an example of what we did. This is on the left-hand side is what the Everglades used to look like. The study area on that figure is in white dashed lines. The current system shows that same study area, no longer part of the Everglades. That's Miami, the Miami-Dade area. And within that Miami-Dade area, if you look at the image to the right, there's all these dots and all these numbers. There's about 200 water control structures in there that we have the option of modifying as part of a restoration effort to decrease the salinity and increase the hydrologic performance of the ecology around Miami. So when you take all those options that you have, you give it to all your stakeholders, you sit down, you basically do the same thing, you sit around in a round table, and you design a bunch of options, a bunch of scenarios, and I'm showing you two different scenarios based on the legend to the left. And it's, of course, very complicated, and we have the model that can handle it. That's the key. You have to have a model that everyone buys into. Everyone agrees that this is the tool you're going to use. And if you look at just one of these options and you focus in on that Miami-Dade County and you compare the configuration to doing nothing, that's what that image is on the bottom left. It's showing in blue that the ponding depth will increase on average by 1 foot, which is what we want. If the system has dried out, the whole restoration effort is to increase the water depth. So this configuration works. The advantage of doing this type of participatory modeling is you get even more information than you thought, and you can look at the big, you can look at the big picture. So you can compare a dry year to a wet year looking at the ponding depths. And then you have a set of performance measures and targets and goals, and you pick the scenario that works the best. We use an optimization program, but based on what I've been hearing today from all of you, that's your next step. You need to take all those models that you've been working on. You need to agree on which ones work the best And then you need to develop an optimization routine to figure out what type of farming practices will optimize the reduction of phosphorus. So finally, the strengths and weaknesses of this approach. Every model, every effort that we do has weaknesses and strengths. So the first one is that it creates a forum for stakeholder participation and collaborative learning. But stakeholders are not always prepared or willing to participate. It builds on a common understanding of the issues and increases trust. That is the key thing that I'm seeing here among you. There's a large amount of trust. There is not a lot of trust in Florida. And one of the reasons is because there is policy, there's government policy that actually limits stakeholder participation. The strength to identify research and monitoring requirements, but you need to have appropriate participatory models, and you can't use ones that are weak, or you can't, and if you don't even have them, then you're in trouble. And then finally, it builds consensus and reduces the probability of litigation, but at the same time, doing this is costly and time-consuming. Thank you.